Hello class, this is Stat 1200. I am your instructor William Buellman, and today we're covering section 4.3, conditional probability and the multiplication rule. The objectives for this section are to be able to compute conditional probabilities, to compute probabilities by the general multiplication rule, compute probabilities by the multiplication rule for independent events, and compute the probability that an event occurs at least once. Approximately 15% of adult men in the United States are more than 6 feet tall. Therefore, if a man is selected at random, the probability that he is more than 6 feet tall is 0.15. Now assume that you learn that the selected man is a professional basketball player. With this extra information, the probability that the man is more than 6 feet tall becomes much greater than 0.15. A probability that is computed with knowledge of additional information is called a conditional probability. The conditional probability of an event B given in event A is denoted P B given A. P B given A is the probability that B occurs under the assumption that A occurs. The probability is computed as, so P of B given A is equal to the probability that A and B happen divided by the probability that A happens. Here's our first example. Consider the following table, which presents the number of U.S. men and women in millions, 25 years of age or older, who have various levels of education. A person is selected at random. So we can see here in the table, men who are not a high school graduate, there's 14 million. Women who have a bachelor's degree, there's 19.2 million, and you can see the rest. So the questions we're going to ask are, what is the probability that the person is a woman? What is the probability that the person is a woman with an advanced degree? And the final one, what is the probability that the person has an advanced degree given that she is a woman? First, we need to compute the total number of people in the study. So the first, we're going to compute the men, which is equal to 14 plus 29.6 plus 15.6 plus 7.2 plus 17.5 plus 10.1, which equals 94 million. And then the women, which is equal to 13.7 plus 31.9 plus 17.5 plus 9.6 plus 19.2 plus 9.1, which gives us 101 million. So there are 94 million men and 101 million women. So the total number of people is 195 million people. We can now compute the probability that a randomly chosen person is a woman. So the probability of woman is equal to 101 over 195, right? Because there was 101 million women and 195 million total people. So the probability is 0.5179. So that is the probability that a randomly selected person in our study is a woman. For the second question, the number of women with an advanced degree is found from the table, and that's 10.1 million. The total number of people is, again, 195 million. So the probability that we choose a woman with an advanced degree is 10.1 divided by 195.0, which gives us 0.05179. That is the probability that a randomly selected person is a woman with an advanced degree. So for number 3, we're going to use the general method for computing conditional probability. that we showed before. So the probability of an advanced degree given woman is the probability of a woman with an advanced degree over the probability of being a woman. So we're just going to use the probability of a woman with an advanced degree, which was 10.1 over 195.0 divided by 101 over 195.0, which equals 0.1. So the probability of picking somebody with an advanced degree, given that we know that they're a woman, is 0.1. The general method for computing conditional probabilities provides a way to compute probabilities for events of the form A and B. If we multiply both sides of the equation by the probability of A, we obtain the general multiplication rule. So the general multiplication rule for any two events, A and B, the probability of A and B is equal to the probability of A times the probability of B given A, or the probability of A and B is equal to the probability of B times the probability of A given B. So you can use either one of these. It just depends on what information you're given, and you'll pick the appropriate rule based on that. Example 2. Among those who apply for a particular job, the probability of being granted an interview is 0.15. Among those interviewed, the probability of being offered the job is 0.35. Find the probability that an applicant is offered a job. We know that being offered a job involves two events. First, you need to be interviewed. Then after you've been interviewed, you have to be offered a job. So we can use the general multiplication rule. So using the general multiplication rule, we obtain the probability of being offered a job is the probability of being interviewed times the probability of being offered a job given that you were interviewed. And the probability of being interviewed, again, was 0.15. And the probability of being offered a job given that you were interviewed was 0.35. So our probability of being offered a job is 0.0525. So that is the probability of being offered a job. Two events are independent if the occurrence of one does not affect the probability that the other event occurs. If two events are not independent, then we call them dependent. Example 3. Determine if the following events are independent or not. In other words, are they dependent? A college student is being chosen at random. The events of being a freshman and being less than 20 years old. So is being a freshman and being less than 20 years old, are those independent events or dependent events? So we're going to have to think about that. And then the second one, a college student is chosen at random, again, and the events that they were born on a Sunday and they're taking a statistics class. So is being born on a Sunday and taking a statistics class, are those independent or dependent events? The solutions are as follows. For the first one, the events are not independent. So if we think about being a freshman and being less than 20, do those two events seem related? Yes. Most college freshmen are younger, typically. So if we know somebody's a freshman, the odds of them being less than 20 is greater than if we didn't know they were a freshman. So having the knowledge of them being a freshman affects whether or not we think they're less than 20, so those events are not independent. They are connected. Now, the second one, if I told you someone was born on a Sunday, whether they were born on Monday, Tuesday, Wednesday, none of that has any effect on what classes they're going to take. When the day of the week somebody is born doesn't affect the classes they're going to take. If you were to ask people in a statistics class, you would get a range of values. They all wouldn't be born on Sunday. You'd have some on Sunday, some on Monday, some on Tuesday, and so on. So the day of the week they were born has nothing to do with them taking a statistics class. So those events are, again, independent. When two events, A and B, are independent, then we know the probability of B given A is just equal to the probability of B, because knowing that A occurred does not affect the probability of B. Remember, A and B are not related, so knowing A happened doesn't tell us anything different about B. This leads to a simplified version of the multiplication rule. Multiplication rule for independent events. So for any two events, A and B, that are independent, the probability of A and B is equal to the probability of A times the probability of B. But you have to remember this only works if we know our A and B are independent. Example 4. According to recent figures from the U.S. Census Bureau, the percentage of people under the age of 18 was 21.3% in New York City, 28.6% in Chicago, and 21.0% in Los Angeles. If one person is selected from each city, what is the probability that all of them are under 18? Is this an unusual event? The first thing we're going to do is we're going to say these three events are independent because the identity of the person chosen from one city does not affect the identity of a person chosen from another city. So those are independent events. So we can use the independent multiplication rule here. So the probability that we get someone from New York and Chicago and Los Angeles is going to be equal to the probability of New York times the probability of Chicago times the probability of Los Angeles, which is equal to 0.213, the probability somebody's from New York, times 0.286, the probability of Chicago, times 0.210, the probability for Los Angeles. And when we multiply those together, we get 0.0128. So the probability that we pick somebody from New York, Chicago, and Los Angeles is 0.0128. This is an unusual event if we apply the most commonly used cutoff, which I told you before is 0.05. So since 0.0128 is less than 0.05, this is an unusual event. When we sample two items from a population, we can proceed in either of the following two ways. We can replace the first item drawn before sampling the second. So we take something out, we mark it down, and then we put it back. If we do this, this is known as sampling with replacement. The second option is we take something out, we record what it is, and we set it down, and we do not put it back. If we do that, this is sampling without replacement. When sampling with replacement, each draw is made from the entire population because we took something out and we put it back so the population is still the same. So the probability of drawing a particular item on the second draw does not depend on the first draw. So when we're sampling with replacement, the draws are independent. When sampling without replacement, the draws are not independent because in the first draw we took something out and we've now changed the population for the second draw, so it's now dependent on what we drew in the first one. When a sample is very small compared to the population, so when our sample is less than 5% of our population, a rule of thumb is that items may be treated as independent. Example 5. Items are inspected for flaws by 3 inspectors. If a flaw is present, each inspector will detect it with a probability of 0.9. The inspectors work independently. If an item has a flaw, what is the probability that at least one inspector detects it? The complement of an event that at least one of the inspectors detects the flaw is that none of the inspectors detect the flaw. We use the rule of complements to compute this probability. We begin by computing the probability that an inspector fails to detect the flaw. So the probability that an inspector fails to detect the flaw is 1 minus the probability that they detect the flaw. Which is equal to 1 minus 0.9. That was the probability that they detect a flaw, which is 0.1. So that is the probability that an inspector fails to detect a flaw. The probability that at least one inspector detects the flaw is equal to 1 minus the probability that none detect the flaw. So that is equal to 1 minus the probability that all 3 fail to detect the flaw. Which is equal to 1 minus the probability that the first one fails and the second one fails and the third one fails. Which is equal to 1 minus the probability that the first one fails times the probability that the second one fails times the probability that the third one fails. So what we've been doing is we've just been working through step by step. So first, we use the complement rule here to get 1 minus the probability that none of them detect the flaws. So what does it mean for none of them to detect the flaw? Well, that's the same as all 3 failed to detect the flaw. Well, what does that mean? That the first one failed to, the second one failed to, and the third one failed to. Well, now since they're independent events, we can use the multiplication rule and get to this point. So that's how we've gotten to this point right now. So now we're just going to plug in the numbers. 1 minus the probability that an inspector fails we have up here at the top is 0.1 times 0.1 for the second and 0.1 for the third inspector, which is equal to 1 minus 0.1 to the third power, which is equal to 0.999. So the probability that at least one inspector detects the flaw is 0.999. That is the chance that if a flaw is present, that one of the 3 inspectors will catch it. Have you guys do this one as practice. So pause the video right here. Use the last example as a guide and try and solve this one, and then I'm going to show you the solution. The answer will be shown in 3, 2, 1. So here's the solution to that problem. I showed a detailed solution because I know in the past students have struggled with this idea, so I wanted to show you multiple steps so you could connect the dots. It's very similar to example 5. If you're still not sure, be sure to email me, come in office hours, ask questions, and get this cleared up.